Hello, everyone. Thank you for joining this online session. And I apologize for sending the notice, a very short notice on today in the morning. I apologize about it. I must confess that being by yourself in this country with your wife pregnant is kind of difficult. So sorry about that. I'm really sorry. I would never do that if it was not something important for me or my family. And I really apologize if my my sudden message caused any trouble in your morning and your life. I'm really sorry about it. But sometimes I have to make two decisions, and I really apologize. I didn't want to, but it's something important in my family. If something happens to my wife, of course, and my baby, of course, that would be very sad in my life. So I prefer to be here just in case something bad happens. Nothing wrong will happen probably, but you know, life is uh, life is a complicated place where bad things can happen and good things can happen too, right? So hopefully you understand, and I'm really sorry about it. Um, and thank you, Nathaniel, for understanding. Thank you so much. Yes, she's okay. She has a little bit of pain, but she's fine. Um, and we went 2 weeks ago to the emergency room, and everything was fine, but still she has had some problems. So it's better to monitor her health closely, right? And but thank you, Nathaniel, and thank you for understanding. This is just a special case, and a special scenario. Normally, when I teach, I don't usually change everything in the morning, right? I don't do that. But yeah, well, thank you again. Um, Today, I want to um, I want to explain more carefully or more in detail, right? The question number 9 from assignment number 2. Many people told me that it's confusing, right? And it's okay. Yeah, and I believe it is. When I wrote that piece of exercise, to be honest, I didn't know what to expect, and that's fine. Well, I'm experimenting with new items and new tasks, so and I will make it better the next time I teach this class for sure. But today I want to explain more how you can solve this question, right? So let me share my screen. And let me just go there. That's to number 2. Let me see if you're seeing what I'm seeing here. Yes, perfect. So remember, this is assignment number 2, and you can find this assignment on the website, right? So let me just close some things that I have here. So in this exercise, the idea is to find the best model, right? Select the best model based on the AIC value, right? The Akaike index criterion, right? So in order to do that, you have to think about what is a good outcome or dependent variable for your model, right? That's something that you have to think. And that's not something that comes out of the statistics. That's something that you have to think related to the theory, right? So I noticed that some people, for instance, were added to the model BMI as an outcome, right? I saw that, right? And that's okay for the learning, for learning the process of how to select variables, right? But um, normally, the variables that are here, right, wouldn't be used to predict BMI, right? So some people did this. I have observed different things. And let me just see where I can draw. Let me just draw something right here. Just 1 second. Oh, let me just close this. Right. Let me just go here. I like this tool. So some people were doing a model like this, right? And so actually I should do it, yeah, like this. So you have an outcome that is BMI, right? And so people were adding, like, for example, a Stroop, right, to the model. You were adding, for example, VO2 peak, which is a measure of oxygen in your blood, right? What is the maximum amount, well, not the maximum, but the peak amount of oxygen in your system, right? And also some people were adding OUS, which is another measure of the same thing, right? And other variables, right? And other cognitive variables. Let's call it cognitive variables. Right? And what people were doing, I observed this, right? I have observed this in several assignments. Let me just make it straight. I don't like when it's like that. Yeah, make it straight, please. Yeah. This one right here. And this one right here, right? So some people are running this type of model where they are trying to predict BMI. And I have also observed that some people are trying, for example, yeah, that one is the one that I have observed several times. Some people were using fat total as well. Oh, let me check. Good morning, Jennifer. Good morning. And it was good that you saw my message on time, I believe, for today's class. Okay, so I was saying that I have observed this type of model, or other people were using fat right here, total fat, right, as a possible outcome. So the thing is that mathematically speaking, of course, you will get a result, right? As I said all the time in class, statistical models are like robots, right? They are programmed to do something, right? It's just a machine. But even though you get results, you have to think what you are doing. What is your outcome, right? Even though you don't know as well a lot about the data and the theory behind this data, you should think carefully what you're doing, right? I'm not gonna reduce points if you were predicting total fat or BMI. I'm not gonna do that. It's just I want to clarify that when you are selecting variables, you also have to think what is a meaningful outcome for your model, right? According to theory. And that's important in psychology because psychology is heavily theory oriented, right? In psychology, we even break many assumptions in our statistical models because we believe theory is above the statistical part, which is kind of wrong. But many psychologists and researchers in psychology do that, right? Because there is this level of analysis that we follow where we really care about theory, right? So if you do this type of model, right, what you are saying is that your cognition, right? For example, your ability to block interference, right? When you are reading or you're doing something, or ability of retaining stimuli in your mind, like, for example, memory, right? All these cognitive processes, you are saying that those are predictors of total fat. So you are saying that that the cognitive ability um, would be before the total fat, right? Because there is some sort of causal inference in this, right? So you are saying that first the person was bad at handling interference, at how to deal with interference, and then that person got fatter, right? That's what you're saying. So you have to think, well, can I really hold that hypothesis, right? Can I really hold that? Well, Probably you could, but you will need a lot of variables in the model in order to sustain that hypothesis, right? Normally, what we observed is a different type of model. What we observed in the literature, and let me just probably go here. I'm going to change it here. What we observed is that, for example, Stroop is normally predicted by total fat, for example. Why? Because we have observed that what happens in the body influences the mind. And it doesn't mean that the mind doesn't influence the body. Of course it does, right? But in terms of a temporal relationship, in terms of time, the relationship between variables, I would say that first people gain weight, right? And that develops some sort of special conditions in their bodies, right? Like, for example, diabetes, or for example, high levels of cholesterol, right? All these things that are related to a very high level of fat in the body, right? So when that develops, of course, that happens first, and then your mental abilities decrease. Why? Because your body is more exhausted. So it's hard for your brain to work properly, right? So it makes sense that first people gain weight, and after that, there is an effect on how you answer cognitive tasks, right? So this type of model would make more sense, theoretically speaking. The same happens with BMI, right? If you add into the model BMI instead of total fat, right, it's the same story, right? Why? First, you gain weight, and then you can see an influence on your mental abilities, right? At least that's what we have observed in different studies, right, in psychology. And for the sake of the exercise, it doesn't matter if you've already created a model predicting BMI. That's okay, because the exercise didn't ask you. The question that I'm talking about is this one, right? And in here, I'm not asking you to do something, right, in a specific way. I gave you freedom, and that's fine, right? But you start to find that that's one aspect to think about, right? Now, how to solve this, right? And I observed that some people have problems installing the library mass, right? Let me know if you still have problems installing mass, and also installing the, I believe you will need the library car instead of mass. I think it's the one that you need. I don't know why I added mass here, to be honest. I think it's the package car, the one that you need for AIC. I don't remember. I always get confused between this package and the package car. But I believe it's car, but it's fine. So, given that you have total freedom to estimate this model, right? You can get any variable and see how it behaves, right? So how you solve it is, first, you have to select among these variables one variable that could be your outcome, right? So, for instance, what happens if you use age as an outcome? Does it make sense to use age as an outcome? What do you think, people? You can write in the chat. Oh, Candice is second. Sorry. First, there's a question in the chat. It says, it would make more sense that BMI would impact VO2 peak at those sort of things, not vice versa. Yes, you are right. You are right. Yes, it would make more sense to see an impact of BMI on VO2 peak. You are correct. Yes, Denise, it doesn't make any sense to use age, right? Age cannot be an outcome, right? Because age is something that happens naturally. We get older just because we live longer. So age cannot be predicted. Actually, yes, Rosanna, logic memory would make totally sense. You are right. Yes, logic memory, for instance, yes, totally, Rosanna. Logic memory would be a very good outcome for this assignment. And actually, let me do it right now. Let's select that one. I'm gonna go to, let me just copy this first. Remember that this is how you open the data. right, in R. I mean, just one thing to clarify, one thing to highlight here. For the outputs of my models, I'm using the package parameters, but you don't have to use it if you don't want to. It's just the library parameters creates this beautiful table. That's why I use it. But to be honest, you don't have to use it. I will show you another way. But I love this package because it has a lot of beautiful, beautiful functions that I love when I'm teaching and when I'm creating my reports for reports for my peers, right? I'm working on different projects, and I have to think how I can make beautiful, beautiful and understandable reports. So this is one of the packages that I use the most for that. All right, so let me copy this into RStudio. Just 1 second here to open RStudio. It will take some time. Here it is. Remind me later. Let me delete this part. I was experimenting with something else. So I'm gonna still use the library parameters. So I'm gonna call the library parameters by just pressing Control Enter in this case, right? And remember, here I'm just running R in using an R script. I'm not using Quarto. I could use Quarto for that, but I'm not planning on creating a document, right? In here, I'm just explaining how to solve this question. So this is not a Quarto document. This is something that we call an R script. The R script will not produce a document, right? It will be like a text, like regular text, right? And the machine understands that it's an R an R syntax when you are inside R or RStudio, right? If you are outside RStudio, the computer will understand that that's just text, right? Which is kind of different from Quarto, right? Just to clarify that. Of course, if you take this code that I'm writing, you have to write this code into a Quarto chunk when you are answering this question, right? All right, so we have this. Let me just open the data. Nice. So now we have the data in the working environment, right? It says OUES data, right? And remember, you can use any other name for your objects. It doesn't matter. It has to be a name that you remember what it is, of course. In my case, I call it OUES because in this project, we were focusing more on this measure, OUES, right? So that's why I call it like that, but you can use any other name. All right, so now we need to see the workflow, the process that we're going to follow. So the first step in order to answer this question is to create and actually, no, you don't need it. You actually don't need this, the intercept model only. You only did this. Actually, I gave you an extra step here. But the first step, the very, very first step is to select the variables that are going to be in your equation or your regression model. And so the first step is to run this part. Let me just copy this. So let's call it this. Let's call this first step. In the first step, you have to select the variables that you want, right? And you have the names right here. And remember to write it exactly as they are right here. Otherwise, R will tell you, hey, I cannot find that one, right? So remember that R is very, very case sensitive. So in my model, I want to use logic memory. So let me check if logic memory was already selected here. No, it is not. So let's go and pick logic memory, right? So I'm going to copy this, and I'm going to paste the name right here. What are we doing here? We are using the package dplyr, which is part of the tidyverse package. And we are using the function select. So this function will select the variables that we want to use. in the data set, sorry, in the model. And after that, you will drop all the observations with missing values. Why do we need this step? Well, because given that we are comparing different models, we need to have the same people in all the models. And why do I say that? Let me give you an example. Let me give you an example. And I don't know if that's clear enough or not, but let me go to a spreadsheet probably around here. And I will give you an example of why is that important. So let's pretend, let's assume that I have a data set where I have ID, right? Subject 1, 2, 3, 4, and so on, right? I have 5, 6, 7. This is subject number 7. And this is my participant number 8. And I have different research variables, right? These research variables are going to be columns in my data set. So for example, let's imagine I have, logic memory. Why not? I have logic memory here. I have age. I have, for example, gender, right? And let's imagine I have, VO2 peak, right? A very important measure in disciplines related to health, right? So let's imagine that I have these variables, right? This is a pretend database. And so sometimes I feel like I'm like these people creating content for children when they say pretend. But yeah. So logic memory. So we have some scores for logic memory. So we have, I don't know, 63. We have 56, right? Let's do something like this. Just random data, right? I just needed to explain my point. And we have age. So let's imagine that we have some people with 45, but no, that would be, no, nobody can live that longer. 56, I might have 25, 23, and probably 18 years old. And in gender, I don't know, just numbers representing categories, right? 1, 2, 3, 3, 3 here, probably 4, probably 1 right here, right? And now my score of VO2 peak. And that's a number, I don't remember the scale. VO2 peak goes from, I believe, from 10 to 100, I believe. I don't remember. I don't remember the scale, but I'm going to make up some numbers. I don't remember exactly the range of values right now, right? So let's do this. 12. Now, look at what's happening here. And let me just put NAs here. Remember that in R, NA means missing, right? So let me put just some NAs here. Where should I put? Oh, yeah, let's create some NAs here as well. Like here, for example. Okay, cool. And let me just create this as a table so it looks nicer for the explanation. Let me just go here. No, probably that's fine. So let's imagine that I want to create a model with this data, right? Well, I want to compare different models, right? So let's imagine that in my first model, logic memory is going to be predicted by age and by gender, right? Let's imagine that. In my second model, logic memory will be predicted by all the above, actually, all the previous ones, plus VO2 peak, right? So I have two models to compare, but I have a problem. The missing patterns are different. So for example, if I use age and gender, in my model, I'm gonna be missing different cases. So for instance, in this case, I'm gonna be missing age. So I'm gonna be missing this guy, right? Let's color this on red, right? This guy is going to be missing because I cannot compute a score. I cannot compute the score if somebody is missing an answer, right? Oh, yes, Elisa. Yes, we can meet after class, definitely. Yes, Elisa, we can totally meet. Yes, stay online, and we can meet later. So as I said, we have a problem here, right? We have different missing patterns. So H, for example, if I run the first model, I'm gonna miss, for instance, this one and this one, right? These two people, right? If I use gender as well, I'm gonna be missing this person as well, right? The whole person is gonna be deleted from the model. And this one too, right? She's gonna be, he or she's gonna be missing, right? Then, because I'm adding H, I'm also missing these people right here, right? And I'm also missing these people right here. Now, when I add VO2 peak, there is another problem in my next model. I'm missing case number 2 because that person has a missing value here. So, of course, in the first model, case number 2 was actually part of the equation, was part of the estimation, right? But in my second model, case number 2 is not there, right? So when you compare models, this is something that we call nested models. When you compare nested models, you have to have the same amount of people, the same people that you use for estimating the first model has to be used in the second model as well. Otherwise, you cannot compare the models. Models cannot be compared as nested models if you are using different number of subjects or different number of participants, or some participant is missing, right? So that's a problem. That's why in this data set, let me just go here, I'm dropping all the people who have NA after selecting the variables that I need. By dropping all the people who have NA, I'm making sure that I'm using the same set of values in all my models that I'm comparing, right? And that's why we need this step, because we have a bunch of missing values in this data set. And again, you might be thinking, why this guy doesn't give us a clean data set, right? Because I can do that, of course, I can just clean this for you. But the thing is that that's not realistic, right? Of course, in real life, you have to make these decisions and you have to be aware of missing values all the time, right? I don't want to give you the idea that data sets are clean and beautiful, because they are not. Data is as complicated as the subjects are complicated, right? So if your topic is complicated, of course, you will get a complicated pattern of missing values, right? So in this case, what I did, as I said, was to drop all the people with missing values. All that explanation was because I wanted to let you know, I wanted to explain you why that is important in the topic of selecting new or comparing different statistical models, right? And was that helpful? Does it make sense? Hopefully it does. Okay, so this is my first step. So in here, I'm going to select OUS, logic memory, build to peak, block design, and digit symbols, and heart rate. I'm going to do that, right? And actually, let's add more. That's a few. Let's add age. And of course, we can add gender, or sex in this case, because it's only females and males, right? So let me just run this part. Oh, yes, I need to call the package, actually. Let me just call package tidyverse. 1 second here. Because this function, drop underscore NA, also comes from tidyverse. So you will need tidyverse in order to run the first step, right? So let's run it. Perfect. Now I have a new data set, a new object representing a new data set called OUS data no missing. That's how I decided to call it. You can use a different name, right? And you can see it here. So these are all the variables that I selected, and I don't have missing values, right? I have 108 participants, I believe. Oh no, I have more. 131 participants in this subset of the data, right? Which is kind of fine. It's a good number for a regression model, a very good model. Sorry, a very good number. Now, in the step number 2, right? In this step, and let's call it this. In the second step, we can actually use the function step AIC, which is right here, right? Oh, no, yeah, you need the intercept model. Yeah, I was wrong. In this function, you need it. Okay, so in the second step, you need to specify what's gonna be your null model, right? Or the model that is the worst, right? In this case, the worst model is this one right here. And why is it worse, right? Why is this a bad model? And let me change this one. You remember, our outcome is gonna be logic memory. Why this is a bad model? Well, remember that when I'm using only tilde in the number 1, what I'm doing is estimating only the mean of my outcome. It's just the average value of my outcome. So I'm saying that the worst model that I can fit on this data, that I can estimate on this data, is a model where I'm just estimating the mean, right? It's just the intercept. The intercept is the mean of my outcome. So in this case, given that I'm going to use logic memory, of course, I had to change my outcome for the one that I wanted. In this case, logic memory, right? And by adding just the one here, I'm saying to the function, hey, I don't have any predictor. The only thing I believe is good is the mean, right? It's kind of silly, right? You might be thinking, well, that's very stupid because, I mean, the mean cannot be the best model, right? Of course, we know that. But we need to start to build up our model. So I'm going to give to the function, to this function step AIC, right? I'm going to give this bad model so the function can little by little add variables and compare different models, right? So we are building up our model, right? It's like when you build a house, right? You start from the base, and then you build the walls, and then you build the roof, and little by little you have a house, right? So we are just creating the most basic model possible, right? So this is our second step. Now, the third step, right here, is going to be the estimation of the model. And how are we going to do that? Well, we are going to use the function step AIC, right? Let me just go here. And let me call the package mass. I believe it's mass, the one that I need. I don't remember anymore. Yeah, I think I did right. I think it's mass. Remember, you have to install this package if you don't have it in your R installation, right? In your R environment. And also remember that you can install the packages by going on RStudio, where it says packages right here on the tab, and then click install. And then you can type the package that you need, and actually RStudio will try to guess the one you need. Remember, there are more than 10,000, I believe it's, yes, 10,000 packages online, right? So of course it tries to guess the best it can, right, out of 10,000 packages with those letters, right? So it will try to guess. Sometimes it fails, but many times it's very good. So you can just type the name and you will guess what you want, right? So for example, with the acronym MASS, you will find these matches, right, in the online repository, right, out of 10,000, more than 10,000 packages online, right? So yeah, I'm just calling the package mass because I need to use this function right here, step AIC. That's the one that I need, right? So let me explain you what is happening here. So in this function, we are passing the worst model possible. This is the one, right? Look at this. The name is intercept model. And I'm using the same name here. Why? Because remember, in R, the idea is to create objects, and objects can be manipulated, right? It's like grouping information into one single object, right? This object has a lot of information together, actually, and we just call it intercept model, right? This object has the information about this very bad model, and actually, if you want to see it, you can use the function summary, and then just pass the name of the object that you want in order to get an output. I didn't estimate this one. Look at that. Now, it should work. So look at that. You will get this table. And as expected, the table doesn't have any predictor, right? It's only the intercept. So it's telling me that the average score in logic memory is 13.64. That's the average score in logic memory, right? With the standard error of this, and this is a p-value. This p-value means that it's telling you that this mean is not equal to 0. That's what it's telling you. So it's testing if this mean is equal to 0, and if that difference is explained by chance or not. And of course, the difference is not explained by chance, right? The mean is not 0. That's what it's telling you, basically. But it's no information that we really need because we already know the answer, right? We don't care about the p-value or anything in this model because this is the worst model, right? We don't care about that. And you don't have to show me the output, actually, when you're running the model, right? I'm just showing how it looks like inside the object, right? Okay, so as I said, in this function, we are going to use this object, intercept model. And remember, you can change this variable as you need in your assignment. Let's imagine that you want to use another outcome, a different outcome, right? If you want to use, for instance, as an outcome, let's imagine you want to predict, for instance, delayed logical memory. You can just change it and see what happens, right? Or if you want to predict, no, yeah, that would be the option. Or if you want to use trail A or trail B. Well, actually, don't use trail B. I mentioned that, I believe, here. Oh, no, it's errors, the one that you cannot use. Don't use errors. Yes, those are the ones that we don't need because it has a lot of missing values. So yeah, trail A or trail B should be fine. Yeah, you can use any of these variables. And of course, you could, as I said before in the lecture at the beginning of today's lecture, you could use as an output fat total and BMI, but that doesn't make a lot of sense according to what we know in this relationship, right? Between what happens in your body and what happens in your mind, right? So you could use it as an outcome, but to be honest, it doesn't make a lot of sense. Of course, as I said, the regression model will give you a result. All right. And then we need a second argument in our function, which is the argument scope. A scope is telling to the function the scope of work, right? Basically, that is telling you that the highest model or the most complicated model that this data can run is this one. And the lowest model, or the model that is more basic, is the model with only the intercept, right? Which is right here. So I'm using, again, this tilde one. In that way, the function knows that as the worst model, I'm thinking about a model with only the intercept or the mean of my outcome. And let me modify this because I have different variables now. So it would be OUS, view to peak. waste block. Oh, yeah. Let's use waste block here. Let me change it. OUS, view to peak, waste block, H. Now H is part of the model, female. And waste digit symbol is here too. And heart rate. Yeah, sorry, it's a very long string. Very long string right here. All right. So, in another thing, I'm specifying here the direction. Direction means how do I want to compare different models? And you could compare models building up your model, right? You can start, as I said, from the base and then add one little variable at a time. Or you can start from the top to the bottom, which is weird in the metaphor of a house. It's like starting from the roof and then destroy everything down. No, it's actually good. It's like having the whole house and then you destroy the house by parts, right? You take off the roof, you take off the windows little by little until you get the most basic house you can get, right? So that's something that we call model selection from bottom to down. Or you can use model selection or variable selection from bottom to up, or bottom to top, sorry. However, you can also do both. This function is amazing because you can do both at the same time. So the function will compare different models first by using the method of bottom to top, and then we'll run again the models, right? Comparing what happens when I go from top to the bottom. And it will give you the best model at the end, which is nice, right? So by running this, and I'm gonna press Control Enter, right? That one will give me, and actually let's do trace. Let's do trace true. If you say true, it will tell you this verboise right here, this legend. So it's telling you what models it was actually comparing, right? It's kind of nice. And if you use the function summary from base R, right? You pass the name here. And actually, this is step number 4, to be honest. Fourth step, right? If you use the function summary, it will tell you the output. And it will tell you which variables are the best in this case, according to the AIC. And what we see here is that the only ones that survived the process were heart rate and digit and no, look at that, and digit symbol, which is interesting, right? So look at that, heart rate. I wasn't expecting that. So it's telling me that heart rate is a better predictor of your performance on logic memory compared to VO2 peak. That's very interesting, actually. I wasn't expecting that. And it's telling me that digit the name of this one is digit symbol, right? Digit symbol is a good predictor of logic memory. And that makes sense, actually. So now the fifth step in this assignment, in this question, is to interpret the results. I didn't ask for interpretation, I believe, in the original question, right? Yeah, I didn't ask about it, but it will be healthy if you try to interpret the results, right? So what is happening here? So in the final model, what we see is that we have this slope and this slope right here. We have only two slopes in this case because only two variables survived, right? So only two variables were the best option to create the model that has the lowest AIC, right? And you can see here that it's comparing a lot of models. Actually, it's kind of incomplete. I never understand why it doesn't show the whole process when I do both. It's telling me that deleting this, deleting this. Yeah, weird. I need to figure out how to get the list of AICs in more detailed way. Inside the object, probably we can find it, but we don't have time for that. But it's okay. So this is our best model. So this slope is telling me that for 1 unit increment in 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 logic, sorry, for 1 unit increment in heart rate, logic memory increases 0.05 units. So given that they have a different metric, they are measured in a different range of values, you cannot talk about seconds or anything like that because the data is not in a specific metric. Both variables are measured in a different scale. So the only thing you can say is 1 unit increase in heart rate, right, represents an A1, it represents, sorry, 0. Let's round this to 0.6. Represents a 0.6 unit increment in logic memory. That's how you would actually interpret that slope, because the units are different, right? The same happens for the second predictor, which is digit span. Oh, sorry, digit symbol. I always confuse that one. So for 1 unit, oh, sorry, I didn't mean to do that. For 1 unit increase in digit symbol, logic memory increases by 0.06. Well, let's round to 0.7 units, right? That's what it says. That's how you interpret the regression model when the metric is different. Now, you might be thinking, but why if we standardize the regression? Yeah, we can do that. If you want to if you want to make it more understandable and compare these two variables, right, and see which one has a bigger weight, right, on the explanation, you could do an extra step. We can actually run this model individually. Let's do that. Let's do something called a standard model. Let's call it like that. I'm going to feed this model, logic memory. Right? I'm going to run it again. I know that this is the best model possible. So HR max plus this one right here. And then data is, what was the name? Check. And the model, here it is. Or US data. Right. Now, oh, sorry. Let me just change here something. I can use the function scale right here. This function will change the scale of my variables. It will convert everything into C-scores. Remember the C-scores? C-scores are when you center the observations towards the mean, and then you divide the result by the standard deviation. That will give you a standardized metric for all your variables. So I can use a scale here as well. And I run the model. And then let's get the output out of this model, right? From our standardized solution. And let me just do it again. I want to disable the scientific notation. Um, oh, yes. It was that, yeah. Options. Yeah, I missed the S. So let's do it again. Yeah, look at that. So probably that's better. It's a long number, but it makes sense. So look at what happened here. Let me show you. Before scaling the relationship, right? We got these numbers, and we were only able to talk about the relationship between these two variables with the outcome, right? We were only able to interpret this based on using the word units, right? For one unit increment on this, the other one increments by this amount of units, because they are in a different scale. But now they are in the same scale. In this new solution that I created using the function scale. So now I can read this as a correlation, like it was a correlation. Remember, the correlation is a standardization of the covariance. So now these numbers will range from -1 to 1. If it's close to 0, there is no relationship. If it's close to 1 or -1, the relationship is very strong. So look at heart rate. Heart rate has a relationship of 0.43. That's very far from 0, right? So we can conclude that heart rate is actually having a bigger weight on the relationship of and the relationship between logic memory and some physical activity scores, right? So this one really has a big weight compared to this one, which is 0.18, right? So now I can compare these two slopes. Before doing that, I wasn't sure which one is bigger, because these numbers are metric dependent. So the way we measure heart rate is not the same that we measure, for example, the score in digit symbols. It's a totally different score, right? So we were not able to see which variable is more important. Now we are able to say that. Now we say that heart rate is a way more important variable compared to this one, because it has a larger weight, right? Also, the interpretation is going to be different. Now, let me give you the interpretation of this model. The interpretation would be something like this. For one standard deviation increase in heart rate, logic memory increases 0.43 standard deviations. The same for the other one. For one unit increase in digit symbol, digit number symbol, Jesus Christ. Like that. Logic memory increases 0.19, rounded 0.19 standard deviations. That would be the exact interpretation of this slope, because both are standardized, because they were divided by the standard deviation of the corresponding standard deviation for each variable, right? So now what we have is something similar to a correlation, right? Or at least the interpretation is something like that. Of course, it's not a correlation. I must clarify that. This is not correlation because we are adding more variables to the equation, right? It's something similar because correlation is actually the base, is the root of regression, but it's not exactly the same. But the interpretation can be read as something similar, just as a relationship. Now, we need to add something else to this explanation. It says one standard deviation increase in heart rate. Oh, sorry. For one standard deviation, sorry, this is wrong. For one standard deviation increase in heart rate, logic memory increases 0.13. Yes, it's better if it's written like this. For one standard deviation, Now, you have to say something like after keeping DSS constant or fixed. And the same applies here. After keeping heart rate fixed. What does it mean to keep something fixed or constant? It means that in regression, when you are interpreting this slope, you are saying that you are controlling the effect of the other slope, because this is a multivariate relationship. So in regression, the good thing is that by adding multiple variables, you are also keeping constant the effect of the other when you are interpreting the results. So by adding this part, you are telling to your readers that you are doing a multiple regression model with multiple predictors, right? I will explain more about it later. Well, not today, probably after Thanksgiving. Why is that constant, right? Also, remember that there is another measure that is important in this output, which is the R squared. I don't know if you remember the R squared, right? The R squared is the proportion of variance explained by the model. The variance of what? The variance of your outcome, right? So this model is explaining, well, let's use the adjusted R squared. That one is better. This model is explaining 30% of the variance because the R squared is equal to 0.29. Yes, just keep it as 29. 0.29. That means this model is explaining 29% of the variance in logic memory, which is good. It's actually a good model. Explaining 30% of variability in your outcome is not that bad. Only two variables are explaining 30%. That's good. That's actually telling you that these two variables are actually important for logic memory. They really are. Now, in a real world, you would have a step number 6, right? And in step number 6, you have to answer what the heck this means, right? In other words, how do you explain that relationship, right? Why heart rate is more important than the score in digit symbols in a cognitive test, right? Why something that is just a physical measure, as simple as maximum heart rate, it's a better explanation for what is happening in logic memory, right? Because you as a psychologist might think, hey, but we only work with cognitive variables. We don't care about too much about physical activity or physical variables. But, well, this regression is telling you that you should, right? Nothing happens isolated. So whatever happens in your mind is because your body is also there, of course, right? So it's telling us that we should pay attention to physical activity. What it's telling us is that physical activity is a good predictor of your performance in digital memory when you are a senior, right? When you are an aging adult, right? When you are older, you should pay attention to your physical activity because that will increase your cognitive performance, your mental performance, right? That's what it's telling you, right? It's telling us that physical activity matters more than just being good at this test, right? So that's a good finding, right? That's what it means in simple words. And of course, in real life, if you have to publish this, you have to justify your words by citing other people saying the same thing, and right, like saying, yeah, this guy found the same thing that I found. Look at that. We agree on this, right? So that will create theory, right? The next step is actually creating theory or adding more information to the theory that we already have in psychology, right? Or in health related fields in this case, right? But of course, you don't have to do that for the homework, for the assignment, right? This is just something that I mentioned, what would happen in real life, right? Questions so far? Everything good? Let me see the chat. Thumbs up? Yep. I just need to know that you don't have questions so I can move forward to another topic. Um, yep, everything fine? Yeah, okay. I'm going to assume that, yeah, thank you, Nathaniel. I appreciate it. I'm going to assume that everything is fine and this explanation works. And you can ask me questions all the time. Oh, Rosanna, Rosanna is asking questions, yes. Will we need to answer up your part 5 of today? Let me see, part 5. Yes, up to part 5. Yes. Yes, that's correct, Rosanna. Up to step 5. Jennifer's asking, how can we summary a standard model? Ah, do you mean using the function summary, Jennifer? That's what you mean when you write summary, or are you thinking about summary as in English? Ah, okay. So it's right here, right? A standard model, you just have to use the function summary, and you will get this information, right? Of course, I disabled the scientific notation, so you can see it as a big number. I don't know if you saw what I did. I disabled the scientific notation by using options, sideban, just because I wanted to tell you the whole number without scientific notation. If you want to do that, you can do it too. Before running summary, you can run this argument right here, well, this command right here, and that will disable the scientific notation, just in case you were also wondering how I did that, right? I like the scientific notation because it creates short numbers, but sometimes for teaching is better if you can see the whole number. And let me see. Yeah, what other question? Yeah, my pleasure, Denise. My pleasure. Yes, Rosanna, that's okay. Yes, for question 9. Yeah, I understood that. Yes. So, yeah, perfect. Let me see. Should we have a break? Yeah, let's continue just for a few minutes and we can finish early if you think that's fine. And let me just continue. My pleasure, Jennifer. And let's continue with the topic that I left behind the other day, in the other session on Tuesday. Just to finish the idea that I had in mind. And then if I have time, I want to show you a new topic that I want to explain. It's not new, but it's a part that I didn't explain when I had to do it. Let me just go here. So the other day, I was just kind of going through the slides, explaining details about moderation that I didn't explain in the video that I recorded last week. And I tried to emphasize as well some things that probably I didn't explain very well. So as you remember, I was explaining about how to compute the simple slopes, or just that's the best name for that, and how you can actually get this plot right here, right? I was explaining how I did it and what is the interpretation, right? Remember that in this model, we have a moderator, which is social support, right? And our predictor is stress, and our outcome is depression. So what we found out is that when people are high on social support, that's the blue line, right? The relationship between stress and depression starts disappearing, right? It's kind of getting flatter, because it makes sense, right? If you have a very good social support, you might have stress, but you don't develop depression, right? You might have a little bit of stress, even though you have a social support network, but still the relationship disappears, right? Because your social support is good at giving you emotional guidance and many things that happen that are actually related to social support, right? We saw that if you are low on social support, which is this red line here, right, which it represents one standard deviation below the mean of social support, right? When you are low on social support, the relationship between stress and depression gets stronger. And when you are at the mean, right, when you have an average score of social support, it starts also decreasing the relationship, right? It's not as steep as it was before when people were low on social support, right? So I mentioned that after doing the analysis, right, after doing this simple slope analysis and seeing, for instance, the output, right, we were looking at the simple slope for social support when people are close to the mean, right, for the average score. And we saw the value for the simple slope when people are high on social support, which is this number right here. And we saw that the simple slope for people when they are low on social support, right? And what we see here is that the relationship disappears little by little. The slope is smaller, as you can see, right? This is a lower number compared to this one, right? This is smaller compared to this one, and this one is smaller compared to this one. So it's telling us that, as the graph told us before, that the relationship starts fading away when your social support is high. So this is what we call moderation, right? What we are analyzing is if there is any third or fourth variable. It can be, actually, it could be more variables in the equation that are moderators. And what we're trying to see is if the relationship between x and y depends on a third or fourth variable, right? And in this case, yeah, it's totally true. The relationship between stress and depression depends on social support, right? And you can see that the relationship between stress and social support is different at different, the relationship between stress and depression is different at different levels of social support, right? If you analyze different regressions, right, regression lines, and by different levels of social support, you can see that the relationship is different, right? So that's what we call moderation. And as I said in the video, and also in my lecture on Tuesday, this is something that we really use a lot in psychology, because many things that human beings do are moderated, right? Are moderated by many things. Like, for example, take into account the elections, how people decide who is the best candidate, right? Is this effect moderated by something? Oh, yeah, for sure. It's moderated by many things. It can be moderated by how much time do you spend on social media. It can be moderated by if your family is traditional Democrat or Republican, right? That's moderated by that. The relationship, the likelihood of the vote, or how you vote, depends on many things. So the human behavior is actually conditional on many things on the environment, also conditional even on, for example, physical measures, like we saw before, right? Like, for example, heart rate. It's very important for cognition, right? And that could be a moderator for other things. So that's why I wanted to teach moderation, because this will give you more tools to think about your hypothesis when you take the seminars. And if you have more practice with more complicated models, once you do a master's, you have more practice, like thinking twice what you want to analyze and how. All right, that's my idea. I'm thinking about ahead of time. I'm thinking of you doing a master's or even a PhD or being a researcher. That's how I think about you, right? So that's why I give you this. If you ask other professors, they don't teach this content because they believe that this is above your capacity to understand sometimes. I disagree with them. There are ways to kind of have an idea, a broad idea of how you can analyze these things, and that will give you tools in the future to think about your hypothesis, right? Even if you don't remember how to analyze this in the future, at least you know that there's something called moderation, and you could think about variables that could be moderators in the relationship between your X and your Y, right? Now, this part is a little bit more advanced, so I'm not going to go into detail. And this is something called the Johnson-Neyman technique. And in simple words, what it does is to find the region of significance in this moderated relationship. So what it's doing is taking social support, right? And is evaluating the relationship of social support, stress and depression at each level of social support. So at each tiny level of social, so that means that it takes each value in your distribution, in your observed distribution, and it predicts a value. It predicts something. So let's imagine that, I don't know, Rosanna is my data set. So I can get a predicted value for Rosanna, but I can also get a slope for Rosanna, right? I can get a predicted slope for her. So if I do that many times with all my observations, I can get a region of significance. So I can get up to what point the relationship between stress and depression fades away, right? So in this graph, what it's telling us is that all these green line, these are the scores of social support where the relationship of depression and stress is not explained by chance, right? So when you are up to 28, sorry, let me see. Yes, up to 28. No, actually it's up to, it's outside the interval 23. Oh, yes. When you are up to 23, right here, right? This is 23 right here. Up to this line, the relationship is not explained by chance. But when your score in social support is larger than 23, right? It's above 23, the relationship disappears. So this, well, no disappears, it's just you don't have a explanation that is not by chance, right? So after this point, everything is explained by chance. So the relationship between stress and depression is explained by chance. So what does it mean? It means that what we already know, if you have a higher score in social support, the relationship between stress and depression practically disappears, right? It starts getting flatter, right? So we already know that. So if you have a very good social support and your score is very high, you have nothing to worry about. So you might get stress, but you might not develop depression. And I always use the word might or likelihood, because remember, these are probabilistic models. We are talking about something that might happen or might not happen, but we don't know, right? So there's always a margin of error. So I always use the word might, right? This auxiliary is very common in statistics, right? That might or might not happen, right? But as the data is showing, it's very likely that it will not happen, right? If you're very high in social support. And these are the simple slopes that we estimated by hand before. So remember, we did that here. These numbers are actually these ones. 0.6, 0.22, and the other one is 0.14 right here, right? So they are right here. They're exactly the same, but they were estimated using a function from the package interactions, and I used the function simple slopes. And by just running this piece of code, you can get all this information in one single sitting, which is wonderful, right? You don't have to do it by hand. There's always a package in R that will do everything for you, and it will make your life a little bit easier, right? So yeah, I got that plot, and I got these results from this package, and we might use it in the next practice. I'm thinking what we are going to do in the next practice, but probably can add an item about it. You might need to do a moderation model, or at least interpret the results, and I will help you. That's the idea. And yeah, that finishes actually my lecture for today. I wanted to talk more about other things, but I guess we can reserve that for our time after break. So, well, if you don't have questions, you are free to go. But before that, I want to say thank you. Thank you for being here. Thank you for being so patient with me. I really, really appreciate that, believe me. And I'm very thankful that you are here with me. And I want to say that please enjoy the break, enjoy Thanksgiving. It's a very important celebration in the United States. And I hope that you can celebrate with your family and friends and be surrounded by love, right? That's the most important part in life. So thank you. And if you have questions, please stay longer, stay here online, so I can help you with your questions. And one last thing, remember to answer the spot evaluations. That's the only thing that I'm forgetting. On Canvas, for those who were not in class the other day, I explained that if you go to the class right here, go to our shell, you will see a new link right here. It should be working right now for you people. If it's not working, please let me know, because I need to send an email as soon as possible to the administrator and see what happened, because sometimes it doesn't work. So please click here and see if you can access a survey. It's a survey with several questions about me and the course. So please answer that. And well, thank you, Candice. Candice, sorry if I don't pronounce well your name. I don't know how to pronounce it actually. Sorry about that, but thank you. Thank you for your words, and thank you, Denise, for your words. I really appreciate it.